All right, welcome. My name is Ryan Holger. I'm with Temperature Equipment Corporation. This week's webinar is variable speed heat pumps. We're going to focus on the Midwestern climate area, specifically the Chicago area, although I think a few of you guys on here are from Wisconsin, Minnesota, and Indiana, I believe it looked like. So we'll kind of talk about it generically from the Midwest, but my examples are based on Chicago data. But it should all be very similar, and you should get the concepts either way. All right, so the main heat pumps that we're discussing here are the variable speed heat pumps from Bryant and Carrier. The Bryant is the 280 ANV and the Carrier is the 25 VNA. Each of them comes in 4 sizes, 2, 3, 4, and 5 ton. They do not have half sizes. It's slightly less important to have the exact size with a variable speed piece of equipment, although it does not mean we want to grossly oversize stuff and hope the variable speed saves us, because it will not, and I'll talk about that specifically. But we don't have to be quite as precise in our sizing. These heat pumps can be paired up with new indoor units, meaning fan coils or furnaces, or existing ones if the existing ones have communication ability. They have to be able to speak the communication protocol that we've implanted into those furnaces and fan coils for the past, 7, 8 years, either the Infinity language or the Evolution language. And that is because as we change the speed of the compressor, we're also changing condenser airflows, EXD positions, indoor blower airflows, and all these things have to link up. So they have to be communicating pieces of equipment indoor and outdoor, and the thermostat as well. So we'll start off real quick with just giving a quick reminder of what a heat pump actually does, and this will hopefully help everybody understand everything we talk about as we go here. So the first thing is, a heat pump is nothing more than an air conditioner that runs backwards, right? So on this top side over here with the cooling, we have our indoor evaporator coil, right? His job is to suck heat out of the air of our home and then through the refrigerant pipe dump that heat to the outdoors. It is regularly cooler inside than it is outside, but through the thermodynamic properties here, we're able to actually extract heat and dump it outside nonetheless. Well, come heating time, we're going to do the exact same thing, except the condenser and evaporator coils change jobs. So now my indoor coil is literally my condenser coil, and my outdoor is literally my evaporator coil. So my job now is to suck heat from the outside and then dump that heat to the indoors. That's my new job. And then you say, well, it's cold outside. How am I going to get heat and dump it inside where it's already warmer? Well, in the summertime, I'm already doing that. It's colder inside than it is outside, and I'm still able to extract heat out of there and dump it outside. So it's going to work the exact same way, just the range of temperatures is going to be different. Now, obviously, the colder it gets outside, the harder and harder it's going to be for me to suck heat out and dump it into the indoors, so I'll get less and less capacity, and we need to address that with other sources of heat or with appropriate sizing depending on your climate zone. In our climate zone here in the Midwest, it's usually going to mean other sources of heat, at least for this style of unit. So the only thing really different about a heat pump compared to a standard air conditioner is that I'm going to have an extra valve in there called the reversing valve, and his job in life is to do what I just said, which is swap the heating and cooling functions of the evaporator and the condenser. The condenser becomes the evaporator becomes the condenser. So for that reason, for the rest of the presentation, I'm going to refer to them as the indoor coil and the outdoor coil instead of saying evaporator and condenser, because you don't know whose job it is depending on the season. All right, so let's jump into this guy here. All right, so variable speed compression. The idea here is that I'm going to put an inverter on these compressors to be able to throttle the capacity of the compressors. This is not a completely new concept. We've been doing this for well over a decade on certain pieces of equipment. In Asia, they started using these inverters on duct-free split type systems. So you guys are probably used to seeing that now on a duct-free split heat pump. It is almost certain that it'll be an inverter style. Not always, but it probably is going to be. So the whole concept's not completely new. What's really new here is that we're actually putting inverters on regular split systems that I can use in residential and light commercial, as opposed to a duct-free split style unit. So these are these two heat pumps. The Hspf is extremely high. It is higher than any manufacturer in the world. It's 13 Hspf. That's heating seasonal performance factor. That is basically the energy rating for these units. So it's kind of like the SEER, but on the heating side. We'll talk more about that as we go. But these are by far the most efficient, and as you can see there, they're almost 30% more efficient than the next closest competitor's efficiency, and 68% more efficient than the legal minimum that you're allowed to manufacture. So these are very high efficiency type units. We do combine them with gas furnaces in northern climates, either natural gas or propane. Then when it gets really cold outside, and the performance factor of the heat pump goes down, we switch over to the gas furnace. So we'll talk about doing that kind of concept as well. And then towards the end of the presentation here, we'll talk a little bit about dehumidification abilities. As you might expect with a variable speed compressor, I'm able to keep the unit operating more minutes of each hour, which helps me keep my evaporator coil wet when it's in the indoor unit. Keep my evaporator coil wet, and helps me dehumidify better. And as you can see there, up to 60% better dehumidification than a standard heat pump or air conditioner would do. And it's also going to lend itself very well to zoning systems. We'll talk about that at the very end of today. All right, so the dual fuel type system, Bryant and Carrier refer to that as hybrid heat. It's a marketing term basically to take advantage of the fact that people have heard of hybrid cars. If you tell someone you have a hybrid car, they're pretty much realizing in their head that you have a gas engine in that car and you have an electric motor in that car. They may not know how they work or how the car is smart enough to switch between the two, but they know they got gas and electric going on at the same time in the same product. That's exactly what we're doing with these furnace heat pump systems. We have a gas furnace combined with electric heat pump, and we're able to switch between these two fuel sources to optimize which one's better at a given time. So which one is better at a given time? It really depends on your fuel costs, and I'll go through some examples of that towards the middle of the presentation. But basically, when it's milder outside, and for sake of discussion right now, milder we'll define as, say, 25, 30 degrees outside up to, say, 60, 65. We're going to use the electric heat pump. When it is really cold outside, say below 25 degrees, we're probably going to use the gas furnace. And then as the fuel costs change year to year, those numbers in the middle change, right? So last year, it might have been, maybe 2 years ago, we'll say, it was highly probable that I would have turned my heat pump off at, say, 22, 24 degrees outside for one of these variable speed heat pumps and turn my gas furnace on below that. Well, now the cutoff point, because gas is so cheap, now the cutoff point is probably like 34 degrees, right? So that middle area is going to change year to year as your fuel costs continue to change all the time. The more expensive gas is, the lower the cutoff point I'm going to have. We'll talk about that specifically. So the whole idea with the dual fuel system isn't necessarily that the heat pump's going to be the least expensive thing to run. It's going to be the least expensive some times of the year, depending on my fuel costs and my outdoor air temperatures. The idea there is that as the fuel costs change, and they are pretty volatile, especially on the gas side. You guys probably know here in the Chicagoland area, 4 years ago we were averaging $1.07, and this is with all taxes and fees and everything included. And right now we're averaging like 72 cents a therm. So it is pretty volatile. It goes up and down all the time. Electric is a little bit more stable, but it does change as well. So for example, if someone only had a gas furnace and the cost of gas rose 28%, basically it went back to what it used to be, right, a couple of years ago, but my electric cost stayed the same, well then my cost to heat my home would only be a 4% increase instead of a 28% increase. And that's because I'm taking advantage of the fact, well, I'll just run my heat pump at lower temperatures to a point, and then I can't do it anymore. This particular example here is based on a 9 Hspf heat pump, which is a pretty standard entry-level heat pump. But obviously with a more efficient heat pump, then that number will be even less than 4%. So we'll go through some of those examples. First, let's, though, address why people don't like heat pumps in Chicagoland market and the Midwest in general. I shouldn't say in the Midwest in general, because Wisconsin and Minnesota do a crap load of heat pumps, as does Indiana. In fact, Wisconsin and Minnesota are 2 of the top 5 heat pump selling states. So you can put heat pumps into colder climates. But in the Chicago area specifically, they had gotten a bad rap several decades ago, and I'm going to try to dispel some of that now that we do heat pumps again, and we do a lot of them, relatively speaking. So the first thing that people didn't like is that they blow cold air, right? So the colder the outside air is, the less capacity the heat pump has, and then traditionally, the colder the discharge air would be out of your fan coil or your furnace. People don't want to have 88, 90-degree air blowing on them. They can certainly heat their home with 88-degree air all day long, no problem whatsoever, but 88-degree air blowing across your 92-degree surface temperature skin feels cool to you. So they don't like that quote-unquote cold blow feeling. So we got to do something about that, and I'll show you that in a second. I get a comment from a lot of people that, you can't use heat pumps in cold climates. I think I just told you that, Wisconsin and Minnesota are two of the top heat pump states that we ship heat pumps into. So you can certainly do them in cold climates, and I'll talk about how to do that in a little bit. We get the complaint that they're too hard to service. Well, if you think about it, this heat pump is nothing more than an air conditioner, and we're assuming that everybody's techs service air conditioners. So let's only talk about what's different. What's different is I have a reversing valve, right? And that guy's job is to switch from heating to cooling mode and make the condenser become the evaporator and the evaporator become the condenser. There's really nothing else involved other than that. The reason that people have complained about servicing those over the years is because now they have to wire up that valve. So they got to buy a stat that can handle that. They got to pull extra wires from the thermostat to that valve or to the control panel for that valve. And then they have to figure out, is this a normally open or a normally closed valve? Is my thermostat set up for normally open or normally closed? And then get all this stuff wired correctly and then cross their fingers and hope they did it right. When we go to these communicating type systems, all that's out of the discussion. You're not wiring anything to the reversing valve. You're not pulling any extra wires out to the unit. And you don't have to figure out if it's normally open or normally closed. You don't really care. All you have to know is to pull the communication cable from the indoor unit to the outdoor unit, and the unit will configure itself and control the valve on its own without you changing any settings. I think that gets rid of a lot of the service issues. A lot of the service issues have been related to electrical wiring. I've gotten the comment that they're not reliable. I do not know where this has come from. I've asked people several times, and the only comment that any of the techs can give me when they say heat pumps are not reliable is that, well, you run them more hours, so they don't last as long. And that's not even, realistically true. The more you run these variable speed heat pumps, probably the less they're going to fail, right? Because when do mechanical things fail? Mechanical things fail when the metal expands and contracts at joint points and causes fatigue. The reason they're expanding and contracting is because they're heating up and cooling down. Heat up, cool down, heat up, cool down. Expand, contract until something busts. This is true for heat exchangers, compressors, anything like that. Well, with a variable speed product, this guy's job is not to shut on and off 5-6 times an hour. His job is to run continuously all the time and never shut off. And we're going to talk about that a lot in a little bit on how often this guy is not going to really shut off. His job is to run continuously and just ramp up and ramp down. So I'm not shutting off. I'm not cooling the compressor down. I'm not cooling down the heat exchanger surface areas. So I'm not getting as much expansion and contraction. I think you're going to find that variable speed units actually have more reliability and longer longevity, if that's actually a correct statement, I don't know, than standard equipment. We've been using variable speed compressors on some of our commercial variable refrigerant flow systems that we've done here at TEC since 2008. And knock on wood, I do not think we've had a compressor failure yet, and those are all variable speed compression. So I think the more variable speed stuff you have, the longer it's probably going to last. Too expensive to install. The installation effort is identical to that of a condensing unit. There's no additional labor. Like I said, the only thing that there might have been is pulling the extra wires from the thermostat, but that now goes away with communicating stats. It's just 4 wires total for everything, for AC or a heat pump, either way. So the install costs are not more. The only real extra install cost is the higher price of a heat pump versus an actual AC unit, but the labor is going to be identical. And then the payback discussion. The payback is really dependent on the fuel cost, and we'll talk about that in a little bit. Sometimes there is a payback, sometimes there's a small payback, depending on what your fuel costs are going to be. So I'll do some examples on those. All right, so addressing some of those issues, that cold blow scenario, that cold blow happens at 2 times. One is when I can't make enough capacity. 2 is when I first start the unit, I turn on the furnace or the fan coil and start blowing air, and I haven't gotten the indoor coil warmed up yet. So we've solved that quite easily through a control sequence change on these units, and we changed this, I don't even know, 15 years ago probably on our heat pumps. Just we haven't done a lot of them in the Midwest here or in the Chicago area. So the first thing we do is we keep the fan off for the first 30 seconds. We don't even bother turning it on. Keep the fan off, but turn on the condensing unit and start using that to warm up the indoor coil. So when I first turn on the fan, I don't have a freezing cold coil to start with. Freezing cold meaning like 65 degrees. Start off with something warmer like 75, 80, 85 degrees. So when I first turn that on after 30 seconds, I'm going to keep the airflow low at a reduced airflow speed for the next 60 seconds. And then even over the next 3 minutes, I'm only going to go at, this example here showing you 70% of airflow, but it does vary depending on the model of unit that you have. And then eventually I'm going to ramp up to the speed that I need for the airflow that I'm required to provide for that particular unit. So the idea there is let everything get warmed up basically before I blast all that air down at you, so you don't get that initial first cold blow. The other thing that we're doing is that we're trying to keep the airflow as low as possible to keep the discharge air temperature as high as possible. The less indoor blower airflow you have with the same amount of BTUs going through the coil, the higher my discharge air will be. So this blue line here is representing a standard heat pump, right? So that's a standard heat pump. As the outdoor air temperature decreases throughout the day or week or year or whatever you want to say, as that decreases, my leaving air temperature decreases, right? And I get to a point where I drop below 90 degrees and people start complaining. That's this area right here. On these variable speed heat pumps, what I'm going to do is try to keep my airflow as low as possible to keep my discharge air temperature higher. So my goal here is typically 104 degrees is my target. I'm trying to maintain 104 degree discharge air temperature. Now eventually, this unit's not going to be able to produce the capacity needed to get that discharge air temperature, and it's going to have to drop off. So this one here is showing you that happening at like 6 degrees. Some models of unit that may happen at 17 or 20 degrees, but eventually it's not going to be able to do it, and the discharge air temperature is going to drop off. I'm going to keep it as high as possible as long as I can initially. All right, so northern climates, do I really care how far my heat pump can go down? So I'm mainly looking here at Chicago. And then, of course, obviously you guys can see there's other cities on here. So if you're out in South Bend or up in Minnesota or Wisconsin, you can grab another city and kind of look at it for example's sake. This is showing you bin data for the various hours throughout the year. There's 8,760 hours in a year. And right now we're just trying to look at ones that are below 65 degrees outside. All right, so that's all I'm trying to do is look at the ones that are below 65 degrees outside. And that's basically what we defined as the heating scenario. So below 65 degrees, I have 6,000 hours in the Midwest here that are going to be heating. 6,000 of the 8,760 hours are for heating mode below 65 degrees. Clearly, this is a heating-dominated climate. Cooling is basically irrelevant, and all I care about is being able to satisfy my heating from a usage energy standpoint. However, if I look at the number of hours between 30 and 65 degrees, it's 4,500. 4,500 of the 6,000 are above 30, right? So above 30, I can certainly run my heat pump. Even a standard entry-level heat pump, I should probably get very close to 30 degrees and still get full capacity out of that thing. So I can run 75% of my winter heating hours with my heat pump, even with a regular heat pump, let alone a heat pump that's going to be able to do more capacity than a standard one. If I want to take it a step further and look at the hours above 20 degrees, so between 20 and 65, between 20 and 65, it's 5,400 hours of my 6,000 heating hours. That's 90% of my heating season. That means only 600 hours are below 20 degrees. Now, I still have to design your equipment to be able to handle, a 0 degree day or a -5 degree day or whatever your design temperature is, -15 if you're up in Duluth. But I don't have to have it operate at that point hardly ever. That's kind of the most extreme scenario. I don't have a lot of hours in that scenario. Most of my hours are going to be something higher, in this case above 20, and I probably can get it done with just the heat pump and not have to kick on the gas furnace or the electric heater. I got a question from Mike that came in. Can these be used in commercial applications such as VVT? So the answer is yes, you can use these split systems in commercial applications. Yes, you can use them with zoning systems, but you can't use them with VVT branded zoning systems specifically. They would be for use with they have their own zoning system. I'll show you that in a little bit. But they have their own zoning system where the zones communicate to this guy as well to command the speeds of the compressors and airflows. Mike also asks if you can use it on a zoning system, would the discharge air temperature below 90 be fine since you don't want more than 20 degrees above space temp since it would cause stratification? So what Mike's talking about there is heating from overhead systems like you would do in a commercial building. In a commercial building, if you look at the ASHRAE handbook, you don't want to be any more than 15 degrees above the space temperature. So if your space temperature is, say, 75 degrees, you don't want to be any more than 90 degree discharge temperature because it's going to cause the air to stay stratified up at the ceiling and not do a good job of mixing down into the space, and you short cycle your air. And technically you have to take a outside air calculation penalty and provide 25% more outside air requirements than you normally would. It causes a whole big mess. So with these units, we're not controlling discharge air temperature, Mike. We're controlling the comfort level of the zone, and it's generally designed for a residential system. So we're specifically thinking mostly about floor-based heating diffusion, where that 90-degree rule doesn't come into play. So yeah, oftentimes you'd be seeing 100-degree discharge on these units, whereas you might want to stay under 90. However, that's still going to be significantly better than what most people do, which is a regular rooftop unit, which is going to be discharging 120 or 130 degrees all the time. So if I can only discharge 100 or 105, that's actually an improvement, but it's still not ideal in keeping it under 90. Hopefully that answers Mike's question. If not, we can talk about it more later. All right, so showing you pictorially here. On the left side here is heating bin hours in red, cooling is in blue. Basically, each one of these bars represents a 5-degree temperature band of outside air temperature. So if I look at 57-degree band, there's 600 hours. 62 is 700 hours. 47 is 450 hours. So you can see that the bulk of my run hours are this guy area right here, right? So I got like half of my year is more than half my year is jammed into that area, which means I got 25 to 65 degree outside air temperature, which is ideal for a heat pump. Yes, I do have some hours where it gets really cold. I have to deal with that, but those are the exception to the rule. And yes, I do have some hours where it's really hot, so I want to have an efficient air conditioning system. But if I have to choose efficient air conditioning over efficient heating, I'm going to pick heating in the Midwest. I want to get something efficient on the cooling side as well, but it doesn't have to be the absolute best, whereas the heating, it really kind of needs to be. So when we do these heat pumps, and we do them either with a dual fuel system, which means heat pump and a gas furnace, or an all-electric system, which means a heat pump with electric strip heat as a backup, I need to figure out what the balance point of this heat pump is going to be. There are two balance points for each heat pump. There is the thermal balance point. So that's the point at which the outside air temperature is so cold, I can no longer make the capacity that is required for the load of your building at that outdoor air temperature. Then there's the economic balance point or economic break point. That's the point at which the cost of gas versus the amount of capacity and efficiency rating of your heat pump at a certain outside air temperature, what outside air temperature is that where it's cheaper for me to run the gas furnace. So we look at both of these things to decide when to shut off the heat pump and when to turn on the furnace in a dual fuel system. In an all-electric system, we look at these just to see when we have to turn on the electric strip heater, but we do not turn off the heat pump. We continue to run the heat pump all the way down to whatever, 0, -5, whatever it's going to be, because the heat pump is still going to be better than the electric strip heating efficiency. So we'll run the heat pump in conjunction with electric heat, whereas in a furnace, we'll shut the heat pump off and turn the furnace on, because the furnace at that point is more efficient. Additionally, we don't want to be pressurizing the refrigerant system while we're running the gas furnace, because if the refrigerant catches fire, bad things happen. So we want that to not be under extra pressure when we're running the furnace, at least not for extended periods of time. So we'll look at some examples of that on when the cutoff temperatures will be for certain heat pumps. We also want to talk about sizing heat pumps. So normally, when I put a heat pump in, I'm also expecting it to do cooling in the summertime, right? I think everybody's probably wanting it to do that. So normally what I got to do is look at the cooling load and the heating load, and those two are likely not going to be the same BTUs, so I have to pick which one I'm going to size it on. On a normal heat pump, I have to look solely at the cooling BTU load and size it on that, because I don't want to have the heat pump be oversized, because it'll cause it to short cycle during the summer, which will decrease my dehumidification. And even worse, it'll significantly short cycle in the collar seasons, fall and spring, and I will have very crappy dehumidification. The more I cycle my unit, the more oversized it is, the worse my dehumidification gets. So normally we size a heat pump for the cooling load, and we round down slightly to the next whole size. So if I were to do a load calculation and it came out to 33,000 BTUs, right, I would round it down to a 32,000 BTU unit, right? Or rather probably a 30,000 BTU unit, which would be a 2.5 ton unit. That would be the normal way that I would do that. With a variable speed heat pump, we actually do it a little bit opposite. We still look at the cooling load for the sizing, but we round up to the next whole size. That's because the variable speed unit is able to ramp down and reduce the capacity, and so I don't get screwed, if you will, in those collar seasons and in the summer on the cooling mode. being too large. Now, I can't go crazy. I can't take that 33,000 BTU cooling load and put in like a 6-ton heat pump, right? It's going to be way too big, and it's still going to short cycle, because as you'll see in a little bit, the heat pump can't ramp all the way down to 0. It's got a minimum cutoff point on that inverter. We'll talk about that. So all I can do is really go up to the next hole size. So if I had a 33,000 BTU cooling load, I would round that up to a 3-ton system, right? If I had a 37,000 BTU cooling load, I would round that up to a 4-ton system, that kind of thing. So normally you round down it slightly, because you probably have so many safety factors in there, you're still oversized. And with the variable speed, we're going to round up to the next hole size. There's 2 ways to figure out these thermal balance points. One of them would be with the old school way, with the the worksheets. This worksheet is not for a variable speed heat pump. This particular one is just for a standard split system heat pump. You got 4 curves here. You have a 5-ton unit, a 4-ton unit, a 3-ton unit, a 2-ton unit. Then down on the bottom here, you have the outdoor air temperature from -10 to 80, and then up the left-hand side here, you have the BTU capacities from 0 to 80,000 in this particular example, or you can look at the electric on the right side if you want. So in this case, they have chosen a 3-ton heat pump. If I follow that curve along, you can see the colder it gets outside, the less capacity this guy can produce, right? So heat pumps, if you didn't already know, are rated at 47 degrees outside air temperature, and then they also get rated at 17 degrees. That way when you're looking at the AHRI data, you can see how that's going to fall off. So they actually published 2 numbers for you, 47 and 17. This chart here shows you all of the outside air temperatures, between there. But if I was rating it at 47, boom, 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 you'd see right here where my red dot is. That's, approximately 36,000 BTUs. So that's why this is a 3-ton heat pump at 47 degrees. That's how it's labeled. That's how it's, AHRI rated and tested. This red line here is the load of the particular house that I'm going to put it in. So to figure out what that line is going to be, you can either use software, or you can do 2 load calculations, one at your design temp, say 0 degrees for sake of discussion here. 0 degrees, this guy needs 53,000 BTUs. And I could do another load calc and pretend his outside air temperatures were, say, 50 degrees, and plot that line, and then draw a straight line between the 2 of them, right? So I can just pretend it's in a different climate zone with the same house and do the 2 load calcs to see what that line would look like. Or I can use other software tools to do that. I'll show you some of those in a minute. So 47 degrees as it gets colder outside, wherever the heat pump line crosses the house load line, that's when I can't produce enough capacity anymore. So in this case, at, we'll say 36 degrees, where that red dot is, I can't produce enough capacity. So at that point, I need to do something else to help the heat pump out. Either put on a gas furnace instead, turn on a boiler, turn on electric strip heat, something like that to help him out with this triangle right here that I'm drawing. Let me draw it better. This triangle right here needs the supplemental heat right in that space, right there. Now, if I wanted to, I could put in a larger heat pump. I could say put in the 4-ton heat pump. Then instead of 36 degrees outside, it would be, say, 29 degrees outside that this guy would get cut off at, right there where that blue circle is. With a variable speed unit, I can do that. I can upsize a little bit. With a standard, 1 or 2 stage unit, I'm not going to be able to, because it's going to hurt me in the cooling dehumidification time. Mark asks if gas utilities are willing to promote the installation of these units. No, Mark, the answer would be. Gas utilities are not, generally speaking, interested in you heating with electric-based heat. They're interested in you heating with gas furnaces and boilers. So the answer to that is currently no. And I'm not sure why you're asking, so maybe later on you can call me and we can figure out what you're trying to do, and maybe we can figure out a better way to do it. All right. So this graph here shows you a similar chart, but for the variable speed heat pumps we're talking about. If you remember the last one we showed you a second ago there, that was just regular split system heat pump, 2-stage. This guy here is the variable speed heat pump. So in this case, the black line represents the load of this house, right? So this guy is this particular house was done at -9 degree loads. This is probably Wisconsin or something like that. With 65,000 BTUs at a -9 degree day. That black line is his house. This blue line going across here is what would it look like if you put in a standard 3-ton heat pump. The colder it got outside, the more it would drop off, right? And this guy would have a changeover thermal break point at, say, 36 degrees. He couldn't maintain capacity anymore, just like the one I showed you in the last screen. If I were to put in a 3-ton variable speed heat pump, it's this red line right here. Right, and it is kind of a weird profile, and that's because they have weird algorithms that play with the indoor airflows as well as the outdoor airflows and condenser capacities. So it's not a straight line like you see on regular heat pumps. These variable speed ones, each manufacturer has a weird curve to it, if you will. So this one has a plateau on this 3-ton unit. So it starts dropping off a little bit, but then we start increasing the outdoor condenser fan speed and decreasing or maintaining the indoor blower speed to maintain capacity longer. So it ends up being somewhat of a flat line. Instead of 36 degrees, this guy could do down to 29 degrees by putting the variable speed one in. So from 29 to 36 degrees, that outside air temperature band, I can now do with my heat pump. And if I were to look at that real quick, 29 to 36 degrees, that's these 2 bars basically right here. It's probably going to be like another 1,000 hours a year that I'm going to be able to run. If I were to round up, like we said, to the next whole size for this particular house and put in the 4-ton unit, which is this dark blue line, it would look like this. This one has a very weird profile on the 4-ton unit for the Carrier and Bryant ones. And that, once again, that's related to the way they've decided to control the airflows. They could make it a flatter curve or a steeper curve if they wanted to, but they've chose to do it this way, which is just makes it more confusing for me to explain to you guys. But nonetheless, I'm able to continue to maintain above the capacity that I need if I wanted to, all the way down to this point where my red dot is, which in this particular example we'll say is 15 degrees outside. At 15 degrees outside, this guy needs 45,000 BTUs. I can't give him any more than that, so I'm dropping off, which means now only this triangle right here is the part that I can't keep up with the heat pump, as opposed to this triangle right here with the standard heat pump. I'm not very good with the pencil here, so it's kind of sloppy, but you can see what's happening there. I'm able to get more capacity longer into the winter season with the variable speed unit. We actually have a tool, an app that we use to show people this, and that's what this app is right here. So this guy right here is showing you outside air temperatures along the bottom from -10 to 65, capacity up the left-hand side for this particular model heat pump with this particular fan coil that they chose in this example versus a regular 3-ton heat pump system. So the blue line is the regular 3-ton heat pump. This green line happens to be that 4-ton heat pump paired with that specific indoor fan coil. So that one doesn't have that same weird dip like the furnace one I showed you a minute ago, but it does kind of have a flat plateau. So you can see everything between that, where my red dot is, that black-blue intersection, and that green-black intersection, that's all hours that I normally would not have been running my heat pump that I get to run it now. So everything in this green bar, if you will, is now available to me. So from this one goes, we'll say from 13 degrees to 32 degrees, I can now run my heat pump in those temperatures as opposed to just the higher temperatures, which corresponded to me being able to run it about 23% more than a standard heat pump, which was about 1,000 hours in this particular example. Mark is asking, what is the maximum size of rooftop unit that will use this technology? This technology is in split systems currently. This is not in a rooftop unit per se. I'm not aware of any variable speed compressors in heat pump rooftop applications. I am aware of some very large rooftops that we use at Carrier for non-heat pump, for cooling applications that use variable speed compression, or actually more appropriately, they use digital scroll compression, which is similar but different than an inverter. That's for large units like 40 tons and up kind of thing. What we're talking about right now is just 2 through 5 ton residential size split systems. So there's our sizing recommendation chart based on your cooling load tonnage. So if you have a 2-ton load, we would round up to the 3-ton unit. If you got a 2.5, 3-ton unit. 3, go to the 4-ton. 3.5 or bigger, we usually round up to the 5-ton unit. Now, you need to be careful on this. What I'm saying here is your actual cooling load. If you are someone, I'm not saying any of you guys would do this, but that always oversizes your equipment anyway, and you come up with, say, an 18,000 BTU load, and you say, oh, I would have put a 2-ton in, so now Ryan's saying round up to a 3-ton? No. 18,000, if you had that, it would be up here on the chart, because that should only been a 1.5-ton unit. He would be rounded up to a 2-ton, right? So don't put all your safety factors in and then round up like you normally probably do, incorrectly, I might add, and then go ahead and round up again. Don't do that. I'm just saying get the correct load calculation, and then from him you can round up. If you're already rounding up, then don't round up twice. We've had that happen on a couple jobs. We had one guy with a 17,000 BTU load that put in a 3-ton heat pump and wondered why it wasn't helping him with dehumidification because it was cycling. All right, so on the efficiency side, we have to go to the mentality of talking about HSPF instead of SEER. For decades and decades, for outdoor equipment, we've always talked SEER, 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 and that's always been the language. SEER is strictly only used for cooling efficiency. How much cooling capacity can I make at what efficiency when it's 95 degrees outside? That's what SEER does. I don't need SEER for the heating mode. It does not apply to the heating mode. It's not applicable to the heating mode. Having a higher SEER does not necessarily mean that I have high efficiency heating, although they tend to kind of go together a little bit because it's kind of a function of surface area of the coil. But what I want to look at specifically is HSPF. So I want to see how efficient it is in cooling. I look at SEER. How efficient I want on heating, HSPF, heating seasonal performance factor. Those two things work the same, HSPF and SEER. Just one of them is done for heating mode at 47 degrees. One of them is done with SEER at 95 degrees. And the reason we got that 47 degrees, by the way, is it represents approximately the same amount of BTUs that I would need on a 95-degree day for cooling. So 95 and 47 are kind of inverses of each other for heating and cooling. And we rate them again at 17 degrees outside just so you can see what happens as the temperature drops outside. So we got to start talking about HSPF. So kind of to explain what that really kind of means. Like I said, heat pumps are rated at 47 and 17 degrees. And those are specifically referred to the E points and the H points on the rating chart. So you could, have anywhere from A through Z or whatever, and they represent different outside air temperatures. But those are the two that every single heat pump manufacturer utilizes. So in that HSPF calculation, not only do we take into account the efficiency of the unit operating at that outdoor air temperature, but we also take into account the cycling losses. So as the compressor turns on and off, just like we do in the SEER, right? If I don't have full load, I got to cycle my compressor. Same thing happens in heat pump. So that gets added into this formula. I have to add in the defrost, right? So as I'm continuing to make my outdoor unit an evaporator, I have the potential to condense on the evaporator surface area. And if I condense and it happens to be less than 32 degrees outside, well then obviously that condense is going to freeze, or it's going to turn to frost, we call it. So we have to defrost it. The way we defrost a heat pump is to basically run it as an air conditioner for a little bit, which means the outdoor unit becomes the condenser again, the indoor unit becomes the evaporator. I suck heat from inside your house to thaw out the coil outside, and then I stop that process and go back to heating. Well, obviously that's a little bit of an energy penalty to me, and that defrost cycle has to be included in here. And then, depending on how I've sized your heat pump, I also have to kick in auxiliary heat, whether that be an electric heater or a gas furnace or whatever it is, to make up the difference in BTUs outside. So that has to go into the formula as well. So the HSPF number kind of takes into effect all of those things. So his job is really to represent to a homeowner how efficient that this piece of equipment is going to be when it's actually operating. At least that's kind of the goal of the HSPF. I'm sure it's not a perfect formula. Mike asks, how does the defrost cycle and requirements differ from a staged and variable compressor? Is there more or less defrost required? That's a great question, Mike. The fact that we have the variable speed compressor does not necessarily mean that we're going to have more or less defrost required. However, because we have that variable speed compressor, we put a bunch of intelligent DDC controls in these units. And because we have those controls, instead of doing normal defrost, which is that if it's below, say, 35 or 36 degrees outside, we assume it's a freeze potential. And we will then allow a timer to cycle on the defrost mode based on a timer for X amount of minutes each hour. That's the old school way of doing it, that they did it in heat pumps forever and ever. With newer units, with the smarter controls, we have the sensors on there to look at the outside air temperature and to look at the saturated condensing temperature. And then we can calculate if it's actually going to be a frost scenario at that moment in time or not, and only enable the defrost cycle when I'm actually going to witness frost on the unit. So I'm actually able to do less defrost mode than normal, but it's not necessarily because I have the variable speed compressor. It's because I have more intelligent control system to go with that variable speed compressor. I'm just basically adding some more sensors to look at that. So these units automatically do that. They track those temperatures and saturated condensing temperature and outdoor temperature, and use that to decide if they're going to go into the defrost mode or not. So that is a benefit to this particular unit with the HSPF calculation. The auxiliary heat is a benefit to the HSPF calculation because we're able to provide more capacity than a standard heat pump would have been. Right. So if I went back to this chart here, And forget about the oversizing comment for a minute, the upsizing comment, because that's not going to really affect the Hspf calculation. But the red line for the variable speed versus the blue line for the fixed speed, I have more hours here that my heat pump can do a little bit more of the work, right? It's not, a huge amount. It's this amount right here, right? But that's going to help me with my using less auxiliary heat, because this area right here with a standard heat pump, I have to do auxiliary heat. With the variable speed, I do not have to do it. So that's going to help my Hspf calculation by the fact that I don't have to run the auxiliary heat as much. The cycling is definitely benefited on by the variable speed compressor. There are cycling losses every time I turn this unit on. It's going to take X amount of time to go from 0 to 60 miles an hour, right? To get this thing started, get the coil heated up, and actually start producing heat. So the more often I cycle the piece of equipment, the less efficient it generally is. And that's true of just about everything, whether it's a gas valve or a compressor or a pump. Generally, if I cycle it, it's probably not going to be quite as efficient as if I can keep it running and just modulate it. So that's directly affected by the variable speed compressor. The defrost improvement is a function of the controls that I'm going to have on these guys. And the auxiliary heat is a benefit of, it's actually a benefit of the increased coil surface area. These units happen to have more coil surface area than other units. That's why I'm getting less auxiliary heat, because I'm able to get more capacity out of it. Mark asked, what's the cost of a 3-ton hybrid system versus a standard furnace and AC? I don't know that off the top of my head, Mark, because I'm not involved in the sales side of the world here, but I can get that information and we can calculate that for you. Putting in a hybrid system versus a standard AC system is not that much more money. However, if you're going to put in a hybrid variable speed system, it is going to be more, probably $1,000 more or something like that if I had to make up a number off the top of my head. So just going to a heat pump is not a huge price increase. It's more, but it's not huge. Going to a variable speed heat pump is a pretty large increase. So if you want to compare this heat pump to other heating technologies, Hspf is fantastic for comparing one heat pump versus the other heat pump, but it's not really useful for comparing technologies to each other. So if you haven't realized what the AHRI has done, which by the way is a collection of all the manufacturers, every type of equipment they've developed a rating system for, but because it's specific to that type of equipment, you can't compare things easily. So it's not easy to compare the AFUE of a furnace to the Hspf of a heat pump to the COP of a geothermal system, to the SEER of the air conditioner, to the EER of the commercial air conditioner, to the IPLV of the chiller. They all have their own system, and there's no way to compare these directly. So the best thing you can do is to convert everything to COP, coefficient of performance. It's not a perfect way to do it because it doesn't take into account all the cycling that some of those other formulas take into account, but at least you can kind of get a rough comparison of one technology to the other. So when we compare these variable speed heat pumps to geothermal systems, that's what we have to do, is look at the COP data that we can get from the manufacturer at the various outdoor air temperatures. So obviously the colder it is outside, the lower the COP is going to be. So not only do I lose capacity, but I also lose efficiency when it gets colder outside. A COP of 1.0 would mean that every kW that I bought from the power company got turned into usable electric heat at the site, or excuse me, usable heat at the site just in general. So generally speaking, electric heat roughly is a COP of 1.0. It's basically perfect, right? Every kW I buy pretty much gets converted into electric heat that heats my building. Whereas if I have a furnace or a boiler and it's, say, 95% efficient, that means 95% of it goes into the building, 5% goes up the stack. My COP is roughly 0.95, right? So electric resistance heat is always going to be more efficient than any combustion appliance that you could possibly have. It doesn't mean it's cheaper to run. It just means it's more efficient, right, at the site. Heat pump's a little bit different. So my heat pump, or any heat pump for that matter, is going to have a COP that's higher than 1. I just said 1.0 is perfect. Everything I bought from ComEd or whoever got turned into usable heat. But I'm showing you here COPs of 3.5 and 2.5 at different outside air temperatures. This is 17, by the way, and this is 47. Well, how the heck can I have a COP that's higher than 1 if 1.0 is perfect, right? The difference here is that with the heat pump, I am not paying to burn some kind of fuel source to make heat. What I am doing here is I am paying to move heat from outside to inside. I am pumping the heat from the outdoor air to the indoor air. I am not paying to create the heat, right? So that's really the difference. I'm just paying to move it, and that's why the COP can be higher than 1. If you were to take your SEER, EER, or IPLV of your cooling equipment and convert it to a COP, you would find that it is also higher than 1. An air conditioner is more efficient than a furnace, given amount of energy per BTU of heating cooling effect. Doesn't mean it's cheaper to run, it just means it's more efficient. So your typical air conditioner, air-cooled, is going to probably have a COP of like 3 or 4, right? So that's kind of the deal there. Heat pumps are air conditioners running backwards. The COP is always going to be higher than 1. The most efficient way to heat a building is definitively with a heat pump. Doesn't mean it's always the cheapest, depending on how much gas costs you. Now, there's different versions of heat pump, regular versus variable speed air-cooled versus geothermal, right? Air-cooled versus water source. We've got different ways we can use a heat pump and different types of heat pumps, and those have different efficiency levels. It's pretty hard to compare air-cooled versus geothermal, but there are some tools that we can use to do that. First of all, we got to stop looking at the Hspf of the air source heat pump. It's really only good for comparing a heat pump to a heat pump. We got to look at COP, and we got to look at the COP at different outdoor air temperatures, and then look at the geothermal COP at different groundwater temperatures. Geothermal in almost every scenario is going to beat the best variable speed air-cooled heat pump. All right, I'll just tell you that off the bat. You'd have to put in a pretty crappy geosystem and very poorly designed a loop in order for it to lose that fight. So the geo is going to always be more efficient. However, the first cost of the geo is fairly high versus the relatively low variable speed heat pump first cost. So there's a trade-off to be had there. And truth be told, almost all the variable speed heat pump jobs that we've done in the past year and a half residentially, almost every single one of them started out as a geothermal job, and then somebody got the $70,000, $80,000 price tag for their McMansion to dig the geo wells, and they said, oh crap, what else can we do? And this has been kind of the plan B type thing. If you want to do geo, that's great. We're all for that. We do a lot of geo systems here as well, but if they can't afford that, then this is kind of like their plan B. So it could be an upgrade to a regular system, or it can be a downgrade from the geo system. If you want to compare them to each other, you got to go to COP, and you're probably going to have to put it in some kind of modeling software that can use the various COP inputs from both of those products at the various outdoor and ground temperatures. So here's some of the ways that we compare these systems to other systems. Since we're talking about geo specifically, these are really the ones that we use in our office to compare a geo system to a variable speed. And I use the Energy Auditor from Elite just because I happen to own a copy of that for free and I somewhat kind of know my way around it to use it. But there's other ones out there as well. But you can compare in these software packages air source versus water source based heat pumps. If you're just trying to compare the heat pumps to furnaces and things like that, there's a couple ways we can do that. Obviously, we can still use the Energy Auditor from Elite if you want to. There's also the Gizmo tool that some of you guys use. It's a home energy auditing software package that we provide to our residential dealers for free, and you can compare in there AFUE versus SEER versus HSPF and all that kind of stuff. There's also another one here. This one is free through Bryant and Carrier, online Opcos calculator. It is the least detailed of all of these guys listed here, but because of that, it's a quick, 3-5 minute type tool. So if you want to just punch some numbers in to get an idea if this is even a conversation you should have with a particular end user, this is probably the right way to do it. And then as you go further along in a project and want to do more detailed analysis, one of these three guys in the middle is probably the way you're going to do it. So for today's purposes and time, I'm just going to show you the online Opcos calculator just to give you some ideas in your head. I'll show you 3 different examples real quick of natural gas, propane, and then electric. So just to give you those examples here, this particular one is similar to the drawings I showed you earlier with the charts. This says 65,000 BTU heating load, 30,000 BTU cooling load. The zip code is where I'm sitting at here at my desk in Melrose Park. Gas cost. I should have updated the gas cost. This is from about a year and a half ago. Right now, if you were doing this today, I would use 80 cents a therm. Your gas cost, and when you're doing any analysis for customers, don't look at how much they pay for gas or kilowatt hours. Take the whole bill, the whole dollar amount, and divide it by the total consumption, and then you'll get the total dollars per therm and the total dollars per kilowatt hour. Because if you just look at your gas cost, you may be paying like 40-some cents a therm, but once you put in the fees and distribution charges and taxes, it comes out to more like 70, 80 cents right now. And electric side, similar thing. Right now, you're probably paying 11 cents when you take in and everything averaged in. Maybe you only pay 6 cents per kilowatt hour, but by the time you add the distribution costs and all that and average it in, it's probably more like 11 cents. So I apologize for having these older numbers here. I'll try to convert them in my head as we're talking. So this particular tool allows you to compare 4 investments. The first one is the base system. So normally what you'd put into that guy would be whatever they own today. However, for today's purposes, I did not do that. I put in a 13 SEER 80% system, just a basic entry-level system. If you're replacing something they put in 20 years ago, it's probably going to be 8 SEER and, I don't know, 70% AFUE or whatever it was back then. But today I'm not doing that. I'm not comparing it for an end user. I'm comparing it for you so you can see this system versus better systems. So this guy is probably the worst unit you could buy today in terms of efficiency, 13 SEER, 80%. If I were to compare that to a top-of-the-line system, this one happens to be 18 SEER, 97% AFUE, that system is going to save $600 more than the basic entry-level system, right? And you can see here how it breaks down. $200 is cooling, $1,300 is that is heating, or you can look at gas versus electric if you want. System number 2 choice here, that guy is a regular 3-ton heat pump with a 97% furnace, so a 13 SEER heat pump, 8 Hspf, combined with a 97% furnace, and that guy's going to save me $676, slightly more than the regular split system would have been, right? And then my last choice here is the variable speed one. This is a variable speed heat pump with a 97% gas furnace. This guy is going to basically be 17 SEER, in this case 11.4 Hspf. I know I said before that it's 13, but if you recall that was for the 3-ton size. I'm happening to use a 4-ton here, so it's not quite as good as the 3-ton. And it's going to save $850 versus a regular entry-level system. So that kind of gives you an idea there of some of the savings, cost differences, and what they might be. Right now, if I was to put in 80 cents and 11 cents as my fuel costs, my guess is that this guy would probably go down to about $600, and this guy would probably go down to like $580. I'll make up a number. It would not be an awesome story because gas has been so cheap. But once gas goes back up above 90 cents or 95 cents a therm, then the math switches back in favor of having a heat pump again. All right. The other thing I want to point out on this tool is what it does for you is that it also calculates the thermal break point and the economic break point for you. So the thermal break point there is telling you on the regular heat pump, when it's below 41 degrees outside, this heat pump is not going to be able to produce the amount of BTUs required at that particular outside air temperature. By the way, this load on the left side is 65,000 BTUs on a design day, which for that zip code is probably minus 4 degrees or something like that. So he's saying, below whatever 41 degrees, I can't produce the, say, 32,000, 30,000 BTUs that you would have needed. On the variable speed heat pump, this guy's telling me, well, when I get down to 17 degrees, this particular heat pump, 17 and below, he's not going to be able to produce enough BTUs to heat your particular space with your particular zip code and requirements. So that's thermally when these guys would have been. So that's the same as that worksheet I showed you. This is just on a software tool. Then it also gives you the economic breakpoint, right? So what that guy is telling you there on the economic breakpoint is, well, based on the fuel costs you put in this case, $1 a therm and 10 cents a kW, based on those fuel costs, at 31 degrees, the regular heat pump, it'd be cheaper to turn it off and put the furnace on when you get below 31. But this variable speed one, when I get down to 23 degrees, it'd be cheaper to turn it off and put on the furnace. So I'm getting an extra 9 degrees of outdoor air temperature that I can operate in heat pump mode at. More efficiently, 8 Hspf versus 11 Hspf. So that's really kind of your energy benefit for this guy, is that difference right there. So on this system here, I have to set up your thermostat to change over at 41 degrees. Because at 41 degrees, I can't keep up anymore. So this economic one didn't even come into play. But over here on the variable speed unit, I have to set it up for 23 degrees. Even though I can make enough heat down to 17, when I get below 23, financially, I'd rather just run the gas furnace, right, on a dual fuel system. If we look at a propane example, in this case, I got propane in here at $2.30 a gallon. My guess is it's probably more like $2 or $2.10 right now, and electric is probably 11 cents or so. So this one's pretty close. But you can see that the dollar amounts get much larger because it costs a lot more to heat with propane. Propane or oil, if you got people that use oil still, And that oil cost is not realistic. I didn't put the correct oil cost in. That's more like $4 a gallon. But propane and oil are very expensive ways to heat a building. So if you got somebody with propane, it kind of starts becoming a no-brainer. You can look at the thermal breakpoints. They're the same as with the natural gas furnace, 41 and 17. So 17 for the variable speed unit. But I can be more cost-effective running the heat pump versus propane gas all the way down to -18. So if it's below -18, run your propane furnace because my heat pump finally dropped below 1 COP is basically what it's telling you there. Now, of course, below 17, I'm going to have to do something because I can't keep up thermally anymore. But you can see economically how it's a huge impact, and then I'm basically saving $3,000 over a regular propane system. But a regular propane system for this guy was costing him $4,000 a year to run, so it's pretty extreme. Then the last scenario here, would be, I'm sorry, I'm switching around too fast on you. Would be electric heat. So same kind of thing. In this case, when I get down to 18 degrees, I'm saying, okay, I thermally can't keep up below that. And by the way, these are different. The gas furnace and natural and propane had the same thermal breakpoints because they're the same furnaces, literally the same model numbers. But the electric heat, no gas building is a different number. Even though I use the same heat pump, I use a different indoor unit. I use a fan coil instead of a furnace, which has different pressure drops associated with it, which affects the airflow, which affects the output of the units. That's why it's slightly different. So my thermal breakpoint's 18. It says down to -23. It's more cost effective to run the heat pump. So what I'm going to do in these cases is that I'm going to run my unit, my heat pump, all the way down to -23. I'm not going to shut it off like I did with the gas furnaces. But when it gets down below 18, I'm probably going to have to kick on my supplemental heat and run them in conjunction with each other. So on a gas appliance, I turn off the heat pump, turn on the gas. When I have a gas heat pump, electric heat pump with electric strip heat, I run them both simultaneously when it's cold. So people that have propane, oil, or all electric are very good candidates for a heat pump, especially one of these variable speed ones. People that have natural gas in the Midwest, probably not the best candidates because natural gas is so cheap right now. They may want it for other reasons, which I'll show you here in a second, but it probably won't be for energy reasons. So the vast majority of the energy efficiency is coming from the variable speed compressor, the variable speed condenser fan, and the larger coil surface area. And these coils are now double road coils, so they've got double the surface area that way as well. That's helping out with it. It's also increased the weight, so bring a friend to install this thing. These compressors can modulate down to 40 or 50% of capacity, depends on the size of the unit. The 2 and 3 tons share a compressor. The 4 and 5 tons share a compressor. So the 3-ton unit, for example, can operate down to 40% of its capacity, and it can do that in 1% increments. So it is basically a 61-stage unit, whereas a standard 3-ton 2-stage unit, it can either operate at 80% when I have 1 stage on or 100% when I have 2 stages on. And I don't know of any of the 2-stage units that get below like 60-some% on just running 1 stage. In your head, you probably always thought it was 50% and 100%, but it's really more like 65, 70, 80% is the first stage, and then second stage is 200%. So I'm able to throttle back down to a much lower minimum than I've ever been able to throttle back to before, which keeps my compressor running longer, which keeps my indoor coil wet longer, which helps me out with my dehumidification. So here's the kind of the capacity range on the cooling side. This is a 4-ton example, so you can see he's able to throttle down very substantially. The red line is his maximum capacity, the blue line is his minimum capacity, and he can operate at any point in between those two. So in this example, obviously, let's say it's this is cooling mode at the moment, but if I get above, say, I don't know, pick 82 degrees, I can't modulate below 27,000 BTUs. At that point, I would have to cycle on and off if I had that little bit of a load that day. So generally speaking, I keep this thing running most of the time. So there's some cooling examples. I'm just kind of skip along there a little bit. The idea is that whether it's in cooling or heating mode, I keep the compressor running all the time in the winter, all the time in the summer, and the only time that the compressor is actually going to be shutting off is most likely going to be when I'm mild out. So say between 60 and 75 degrees, because I've throttled back my unit as far as I could, and now I'm at the minimum, and I can't keep throttling him down more, so I got to cycle him on, off, on, off, on, off. So between, say, 60 and 75 degrees, he'll cycle, but above that or below that, he's probably going to be running continuously. This is a unofficial study that was done comparing the variable speed unit versus a regular unit with a whole house dehumidifier. So here's how much water that a 3-ton unit with a whole house dehumidifier installed extra could remove. So 170 pints per day. This green speed unit on its own, without the whole house dehumidifier, is removing 130. So he's doing a pretty good job on that. And he's doing it with a lot less energy consumption. Right? So I'm able to remove more moisture without running more equipment. When you put in a whole house dehumidifier with a regular air conditioner, all you're really doing is adding a second air conditioner and falsely loading it, which is not an energy saving mechanism at all. It's more of a band-aid for someone who's grossly oversized their equipment. So putting in a variable speed unit is going to help out with that. Sound levels are actually very quiet. When we do classes here in our lab in Melrose Park, we have these units installed in our training labs, and we have for the past year and a half. When we do classes on them, we literally stand with the entire class next to the unit while it's running full capacity and have conversations. It's pretty impressive on how quiet these units actually are. Additionally, they hardly ever run at full capacity. They're almost always running at some part capacity because they're seldom ramping all the way up. So it is a very quiet unit, and many of the installs, if they were not a plan B to a geosystem, they were very likely installed because of the dehumidification benefit needed or because people wanted the quietest unit they could get. It is very seldom a discussion of energy. It's usually someone wanting better comfort or better sound or something like that. Actual energy consumption is hardly ever the story, although it is the most efficient unit that we got. So lots of stuff in these units that help out with the sound. There's a muffler on the refrigerant pipe system, so any vibrations caused by the inverter do not vibrate through the pipe and into the house structure. They have the typical carrier fan system design, with the one where the Sikorsky helicopter guys from UTC help them design it to cut through the air better and reduce sound. Obviously, they got compressor blankets on there. We got grommet posts that these guys sit on, so I never have metal to metal touching it. And then additionally, these plates that these are attached to are laminated, so there's no metal there that's touching either. So it actually ends up pretty quiet unit. All right. In the interest of time, I'm not going to go through every single component on here. To show you a couple highlights. So we have an EXV in the outdoor unit. That's an electronic expansion valve. It works like a TXV, except we control it directly with the DDC controller, and it has 600 steps of control. So it's basically a modulating valve. We still have a TXV on the system at the evaporator for the indoor piece of equipment. Excuse me, the indoor unit equipment. This EXV is to be used in the heat pump mode when the outdoor unit becomes the evaporator. Lost my mouse. Hang on a second. All right. We got a charge compensator. That's because we have a different requirement of refrigerant in heating versus cooling mode. So we basically got somewhere to buffer that refrigerant is basically all that's doing. Actually, that wasn't the charge compensator. The charge compensator is the green one in the back, the accumulator. This one is just the muffler. It's highlighted wrong. Got a variable speed compressor with an inverter on it. I'll show you that inverter in a second. And we got some additional sensors out there on the unit that we can record data from and control it a little bit better. So 600-step electronic expansion valve, that's key to controlling this. We modulate the refrigerant through the expansion valve. At the same time we modulate the compressor. At the same time we modulate the condenser airflow. At the same time we modulate the indoor unit's airflow. And we might even be modulating a gas valve on the indoor unit as well. So all these things are kind of working in conjunction with each other. There's the actual inverter on the unit. It is external to the compressor. It's on the outside of the unit. This is the back side over here. So all those heat sinks are on the back side sticking into the airflow. This is the front side of it. It's got a protective cover on it. Down here is the control board that operates this guy and communicates over a 4-wire cable back to the indoor unit and to the communicating thermostat. The inverter takes in AC power, modulates the signal to change the frequency, and then it converts it to DC power, modulates the signal, and then sends DC power to the compressor. So the compressor in this unit happens to be DC. So it's kind of like a VFD, but a VFD would go from AC to DC, modulate the signal, and then spit it back out as AC. In our case, we go from AC to DC, modulate the signal, and continue spitting DC out to the compressor. Every time we switch from AC to DC, it's another loss line point, so we try not to convert if we don't have to, and since we're able to get a DC compressor from Copeland, that's what we've been using on these units. So that's the compressor that we use. It's a Copeland variable speed compressor. It has, for the past 2 years, been an exclusive thing for Bryant and Carrier, but I believe that it's now going to be released to other manufacturers as well. These units can handle low ambient cooling, so if you are putting them into a commercial application, you do not need any additional controls to be able to go down to 0 degrees, low ambient. You probably got to add some wind baffles if you're putting them on a roof. That would still probably be the case. And you do not need a crankcase heater either. So you do not need to add any motor master controls because these already have variable speed condenser fans, and you don't need to add a crankcase heater because we already have a sump heater. The other nice benefit of these variable speed compression units is that we can now reduce the indoor unit airflow more than we were able to do before as well. So they're showing you a typical two-stage heat pump. We go from 1050 CFM down to 840 CFM when I'm only running one stage, because that's approximately how much I've reduced my capacity from 100% to 80%. I reduced the airflow with it. Well, with a variable speed unit, I can actually reduce it significantly more. So instead of cutting it back 20%, you can see I'm cutting it back like 60% of the airflow. Right? So providing less airflow has two benefits. One, it helps me control that discharge air temperature to keep it higher when I need to in the heating mode. It also reduces the sound, and it reduces the energy consumption. This example here is showing you the cooling mode, but the heating mode does the same thing. We throttle back the airflow much lower than we ever were able to throttle it back before on the indoor unit. So as much as a 60% reduction. If we put it on a zoning system, we can reduce it even more than that, because now some of the zone dampers will be shut down, and we'll be able to reduce the airflow for both the zoning needs and to match up with the cooling compression needs and heat pump compression needs. The zoning systems, like I was telling Mike when he asked the question earlier, we do zoning systems on it. The only zoning system you can put on these variable speed heat pumps is the Carrier or Bryant communicating zoning systems. So for Carrier, it's called Infinity. For Bryant, it's called Evolution. Those zoning systems do not have a bypass damper on them. The bypass damper is not only not needed, but it's not permitted because it would fight the variable speed algorithm we have in here. So you put no bypass on here. As the zone damper starts throttling back, we sense that increased static pressure, and we modulate the indoor fan accordingly. And as the indoor air fan modulates down for less airflow, we're also inadvertently putting in caps on the maximum compressor speeds and condenser fan speeds. So it all kind of works in sync with one another. There shows you another example with a 4-ton unit. Same kind of concept, although not quite as dramatic of a reduction as the 3-ton unit, but I think you can still get the idea on how much we can cut that airflow back. Let me see if we had any other last questions on here. Looks like Mike typed in another one. Will the use of these software tools meet the Illinois Energy Code requirement for showing that a system isn't oversized? All right, so in that regard, there's actually two answers to that question, Mike. So the software tools in discussion that I was talking about were the energy modeling tools, but for the Illinois Energy Code, you're going to be looking at your load calc tools. Those same software manufacturers also make load calc tools. It's not technically a separate package. So you have to do a manual J load calculation for the Illinois Energy Code, and then you also have to do a manual S equipment sizing. Manual S is going to have some requirements on how much you're allowed to oversize heating and cooling equipment. So heating equipment could theoretically be oversized by 40%. Cooling equipment can only be oversized by 15%. And that's for both sensible and latent. Each have to be under 15% oversized. So if you're thinking about my discussion earlier about recommending that you round up to the next size, that could be problematic in complying with manual S requirements from ACA. However, those requirements do not seem to address variable speed technology at all. They don't take into account the fact that I can actually modulate this unit down. So they're just assuming you have 1- and 2-stage equipment, in which case you cannot be more than 15% oversized, in which case you could not do what I said and upsize the unit. However, the way I'm looking at it and have been looking at it is that manual S does not address the fact that I have variable speed units and I could modulate them down. So it's not really up to speed on the current technology, if you will. And I think you could probably make a case with your building permit reviewer that and show him on the software tools that you could still meet the sensible and latent requirements at a particular outdoor air temperature with the variable speed unit, even if it is slightly upsized. But you probably would have to show him that at the various outside air points in question, 2 or 3 sample points. But that's a very good question, Mike, because that ACA Manual S does not adequately address what to do with variable speed equipment at all. Same thing with modulating gas furnaces. It does not address how to handle that in that standard. So those standards need to be updated, and I'm sure they will be soon. Any other questions typed in? Let's see. I do not see any other questions right now. If you do have questions, send me a note or call me. My contact info is up on the screen there. I'll leave that up there for a couple minutes if you want to write it down. And then a recorded version of this presentation will be posted on our website later on this afternoon, and anyone's welcome to watch it there. Thank you much for your time, and we'll talk to you guys next week.